Welcome back to the walkthrough of our videos for topic 2, vectors and matrices. This is video 4 and we're on page 9. This is the last little bit of the subtopic, algebra of vectors in 3 dimensions. Previously we've looked at geometric proofs using vectors, but only in 2 dimensions. Now we're going to have a stab at doing things in 3 dimensions. We might start with the example, which is the bottom of page 9 first, because it's in 2 dimensions, and we'll come back to the other example. The top of page 9, it's in 3 dimensions. This example says, the diagram below shows a triangle with vertices O, A, and B. Okay, O is the origin, OA is the vector A there, OB is the vector B there, R is the midpoint of OA. S is the midpoint of OB, there's S. T is the midpoint of A, there's T. Using the vector method, prove that SR, T, and B is a parallelogram. Yeah, excellent. Prove that that is a parallelogram. Well, parallelograms, opposite sides are parallel, so we can prove that. We pretty well show that that thing, SRTB, is a parallelogram. So that means that these sides, RT, RS, SB, ST, we need to start finding them. Let's start with RT. RT, and then we'll compare it to SB in a moment. Okay, RT, how do I go? Well, starting at R and going up to T, I would travel halfway along OA, which is a half of A. And then, so that would give me, that would put me at A. Then to get from A to T, I would go halfway across AB. So amongst this, I'll have to look at what AB is. So that's a half. And AB would be a half. Okay, starting at A. Getting to B, I'd go opposite, negative A direction, and then add B to that. Great. Altogether, that would give me, well, there's a half A plus negative half A plus half B. It would just give me half B. What about SB? Well, you'll never guess what SB is. SB is a half of B. Yes, it is. But that means that RT and SB are the same. That means that RT is, well, not only is it congruent, but it's also parallel. SB is congruent to SB. And RT is congruent to SB. Well, that's handy. Okay, well, I've just proven that these two are parallel and equal to each other. Now, if I could do that to TB and RS, I would be golden. Let's try TB. What is TB? Vector TB. Well, TB would be a half of AB. Agree? That would be a half of, now AB would be negative A plus B. So that would be negative a half A plus a half B. Alright, what about RS? Is it going to be the same? Let's look at RS. So RS, so go from R to S. I could go from R to O, and then from O to S. So by doing that, I'd be going R to O, and then O to S. So RO would be, that would be a half of A, but going in the opposite direction. So that would be negative a half A. And OS would be a half of B. Oh my goodness. Look at TB and RS. That means that TB is not only parallel to RS, but they are also exactly the same. They are. TB is congruent to RS. What does that mean? That means that this side and this side are congruent and parallel to each other. What does that mean overall? I'm thinking that's enough to say that therefore SRTB is a parallelogram. Sweet! Cool. Alright, well what if we go to the example to the top page, which is in 3 dimensions? Does it get much harder? Not really. They're hard enough, these proofs using vectors. But here's a good old favourite that we've grown to know and love. For any rectangular prism, a space diagonal is the line from one vertex to the opposite vertex. Under what conditions would space diagonals OK and JC be perpendicular to one another? Remember, what happens if vectors are perpendicular to each other? That's right, their dot product is equal to 0. Yes. So we need to find some dot products here, which is by far our favourite thing in the world. Okay. Before we start anything, let's assign some stuff to make our life easier. I'm going to say that the vector from O to A, from the origin of A, is equal to A. Just to make life easier. And also say that OC from O to the point C is, what do you reckon? My God, C. OB, let's call that, just for the hell of it, vector B. So that'll save some writing. What do I need to prove? Well, I need to find JC and OK. And I need to show that the space diagonal JC and the space diagonal OK, when I find the dot product, it equals 0. And if that's the case, then they would be perpendicular. Well, there's a bit more to it in this case, but we'll get to that in a minute. It says under what conditions will it be perpendicular to each other? Well, we can come to that in a moment. But all that we need to find is firstly the dot product and show, or work out how it equals 0. Dot product first. Okay, I need to find JC dot OK. So follow my logic. JC, to go from J to C, I would go in the negative A direction and a C and a negative B direction. And from O to K, a bit easier. It would be A plus a vector B plus a vector C. Okay, just divide this into half so I get a bit more room. So up the top, I'm going to expand all of this out and work from there. So when I do expand, I'm going to get a whole 9 terms. So I'm just going to pause and write them out for us. So here I've expanded this out. So the first term I get is negative A dot with A. Okay, that's our first term there. And then negative A dot B, negative A dot C, etc., etc., etc. Then we move on to C, and the fourth term will be C dot A, C dot B, C dot C, which is our third term there. And finally, negative B dot A, negative B dot B, negative B dot C. Now that's similar to things that we've done previously when we talked about 2 dimensions, but it's the same sort of thing that we find now in 3 dimensions. Now some of those vectors are at either 90 degrees to each other or 270. Cos, and remember what the definition of the dot product is. If I have A dot B like that, it equals normal A, it equals normal B, it equals the cos of the angle between them. Now between negative A and B, there's an angle of 270 degrees. Not 90, but 270. But either way, cos of 90 and cos of 270 degrees is equal to 0. So negative A dot B, I can put a big black mark to it, because the dot product, because those things are perpendicular, will be equal to 0. And negative A dot C, you guessed it, 90 degrees between them, or 270, they will cancel out. And so the story goes. C and A, we can cancel. C and B, we can cancel. Again, because there's either 90 degrees between them, or 270. Negative B and A, Gonskis. B dot B, no, there's 0 degrees between them, and cos of 0 is 1, it stays, but negative B dot C, 90 degrees, or 270 between them, it's gone. What does that leave me with? It leaves me with negative a dot a leaves me with negative b dot b, and it leaves me with what else left? Plus c dot c. Okay, now let's just go back to the definition of the dot product and work out what those values are. Okay, so negative a and a, the dot product between them, that would be the norm of a by the norm of a by cos of the angle between them. What's the angle between a and negative a? It's 180. So we're going to put in cos of 180. What's cos of 180? We'll get back to that. Plus, next bit, what about dot product between b and negative b? Well, that would be the norm of b by the norm of b by cos of the angle between them, which is cos, again, 180. And c dot c, that would be norm of c, cos of the angle between them. In this case, it is 0 degrees. What's cos of 180? Negative 1. So this would be negative a, normal of a, normal of b. And this one, negative normal of b, normal of b by cos 180 again, which is negative 1. So it's negative b by normal of b. And cos of 0 is 1, so that would be plus norm of c, or negative norm of a squared, negative b squared plus c squared. Now if JC is perpendicular to OK, then the dot product will equal 0. We just worked out that the dot product is this: negative a squared, negative b squared plus c squared is equal to 0. If I rearrange that, then norm of c squared would be equal to the norm a squared plus the norm of b squared. What does that mean? Well, does that look familiar? A squared plus b squared is equal to c squared. That's a Pythagorean triad. That means that a, b, and c, which is the hypotenuse, forms a Pythagorean triad, which basically means that they can be put into Pythagoras equation like we have here. A squared plus b squared is equal to c squared. A is the length of a triangle thing, c is the hypotenuse, and it fits this formula. And if it does, we refer to A, B, and C as being a Pythagorean triad. And they're able to do that. That's the relationship. So those are the conditions under which OK and JC will be perpendicular. Conditions being that A, B, and C form a Pythagorean triad. And all again comes back to relationships we've already talked about. When vectors are perpendicular, their dot product will be equal to 0. Alright. Okay, we're going to leave this particular video now because this brings us to the end of our first subtopic on algebra of vectors. So when we next start the next video, we'll be on to the next subtopic within this big fat topic of vectors and matrices. The subtopic will be vector and Cartesian functions. Alright, thanks girls. See you on the next one.